In this lesson, we're going to learn about three-dimensional vectors. Now, a vector is one of the most important tools in your toolbox as a game developer. I use vectors every day, and being able to understand these and visualize these is very important. So it's just a skill that you'll get better and better at with practice, and they can also be a lot of fun. So a vector is a line in 3D space. And the simplest way to define a vector is just with a coordinate. If we have this coordinate here, -2, so we go over -2 on the x-axis, we go up 4 on the y-axis, and the z-axis is 0, so it just stays here on the xy plane. If we have that coordinate and we say that's the end point of the vector, and the starting point is the origin, 0, 0, 0, then that forms a line. And that vector has a direction, and it also has a length. We can use the vec3 class to define this. So a vec3, it can be used to define a coordinate in 3D space, so a position, and it can also be used to define a vector, depending on just how we're thinking of it. They're kind of the same thing. We can access each individual value, x, y, and z, independently. So I don't think I'll run this, but if you construct a vector with 2, 4, and 0, and then you say print v.x, print v.y, print v.z, then it will just print out 2, 4, and 0. So you can retrieve the individual components of the vector. So again, it can either be, you can think of it as a point in space if it's a coordinate. You can also think of it as a line from the origin to that point. And so it has a direction, and it also, very importantly, it also has a length, or sometimes this is called the magnitude. Now the vector length is, it's very easy to calculate. There's a formula for it. And I'm not going to ask you to memorize a lot of mathematical formulas, but this is one that you should know by heart. The length of any vector is x squared plus y squared plus z squared, and add those together, and then take the square root of that, and that gives you the length of the vector. So let's copy this code. We'll paste it. And so we're creating a vector. The x is going to be 3, y is 4, z is 0. And here, this is the formula for, this is the same formula that I already showed you. v.x times v.x, that means v squared, v.x squared. v.y plus v.y times v.y plus v.z times v.z, that's v.z squared, and then we're calling the square root function, and that's going to give us the length. And you can see down here it printed 5. So that's 345 is a special value that that has some historical significance. Okay, well, we don't have to do this manually all the time. We actually have a function that already does this. It's built into the vec3 class. We can just call v length, and that will also print out 5. So it's just running the exact same code that I showed you, but it's just a built-in function. So why am I saying that you should learn this? The reason you should learn this is because if you're drawing things on paper, sometimes you'll want to be able to figure out the length of a line in your drawing, and this is how you do it. If it's a 2D drawing, then that means z would be 0, and 0 squared is just 0. So you can ignore the z-axis if you're just drawing a 2D surface. But if it's 3 dimensions, then you need to know this formula. So this is one to definitely memorize. Now, sometimes we only care about the direction of a vector. We don't care so much about the length of it. And we can easily normalize a vector, which means we turn it into a unit vector, which means its length is exactly 1. And we have a built-in function for this already. Let's copy this. And paste it. Okay, so we're constructing a vector that's with length -2, 4, and 0. And then we're converting it into a normal with this normalize method. So the normal, in this case, it's just the same vector, but we shrank the length to be exactly 1. Or you might also increase the length. Let's run this. And let's see. So it prints out the x component is now a lot smaller, -0.44. The y component is now shrunk to 0.89. But they're both shrunk proportionally, so it's still facing the same direction. It's just got a length of 0.999999. That's pretty close to 1. Again, like, computer numbers are not perfectly precise all the time, but if you see 0.999999, that means 1. So it's close enough. So both all the components of the vector got smaller, but it stayed the same. It stayed in the same direction. So if this was our vector to start with, and it had a length of I think the length was 5. No, not that one. But then what happened is we shrank it to be that long. And that's supposed to be drawn so that it's exactly 1 unit long. It might be a little bit short, but you get the idea. So we didn't change the direction of the vector. We just shrank it down. We use normals like this very often. You might have heard of vertex normals, and that tells you which direction a surface is facing at a certain point on the mesh. These are often used in lighting code. It's often used in physics, and you're often doing multiplication with these vectors, and so it's important for them to be normalized so that they don't increase the overall results. For example, if you tried to do lighting with vectors that were not normalized, you would get abnormally bright lights because the resulting brightness would be cranked up because all your numbers here are bigger. Okay. So we can add vectors together and we can subtract vectors from one another. So to do that, to add two vectors together, all you have to do is add their individual components together. So if we want to add a plus b to get vector c, what we do is we set c.x equal to a.x plus b.x, and we do the same thing for y and for z, and that gives us the sum of those two vectors. So here's an example. A equals vec3, 1, 2, 3. B equals vec3, 2, 3, 1. And then we can declare a new vector, c equals a plus b. So we don't have to do this manually every single time. We can just add them together like that. And then this will print out the sum of a and b. So for x, it should be 1 plus 2. So it should print 3. And then for y, it should print 5. And for z, it should print 4. Let's see if it worked. That prints out 3, 5, 4. Okay, so thinking of vector addition in terms of numbers, if you're mathematically inclined, then that might be easier for you. I'm not particularly mathematically inclined, I usually think in terms of geometry. And the easy way to add vectors together using just visually is to just draw the two vectors out and then connect them. So if you're trying to add the vectors 0, 1, 0 and 1, 0, 0, this is going to be the result, 1, 1, 0. So you can add the individual components like we just did, or what you can do is take the first vector, and then at the end of it, take the second vector and just move it right there so that it's like this. And then the sum of those is just going to be the beginning to the end. That's a very easy way to do vector addition. And subtraction is just the exact opposite. If you just take this vector and then to subtract this vector, you would just move it to where the arrows meet and you're going backwards. So you're just adding the opposite vector, and that would give you subtraction. We can also multiply two vectors, and the way we do that is exactly like addition. It's just you just multiply the individual components, and of course we don't have to do this whole thing manually each time. We can just say A times B equals C. You can also multiply a vector by a single number, so B times 2 equals A. That's going to give you the exact same vector, but it's going to be twice as long. It'll still be the same direction, it'll just be twice as long. And when you do that, this is the exact same thing as saying B times vec3 and just creating a new vec3 with using 2 for x, y, and z. We don't have to do this every single time. We can just say B times 2 equals A. I don't think there's really an intuitive way to visualize this really. Not like you can do with vector addition. So scaling a vector, that's what we saw here. A equals B times 2. That just keeps the same direction, but it makes it longer or shorter. You can also do division as well. It's not as commonly used. I don't think I use it very often, but it works exactly the same way. If you multiply a vector by -1, then that will give you the exact opposite vector going in the exact opposite direction. So that's just a special case of multiplication. Okay, now we have two interesting functions for games here. One is the dot product. The dot product is a measure of how similar two vectors are. So if two vectors point in the exact same direction, then the dot product will equal 1. If the two vectors point in the opposite directions, then the dot product will be -1. And if the two vectors are at a 90-degree angle from each other, like these two are, then when you call the dot product function, that will return 0 for these. So if they're the same vector, dot product will be 1. If they're the opposite vector, exact opposite, then dot product will be -1. If they're at 90 degrees from each other, then dot product will be 0. And if it's somewhere in the middle, then the dot product will be a number somewhere between -1 and 1. So the closer it is to 1, the more similar the two vectors are. The closer it is to -1, the more different the two vectors are. Well, this is extremely useful for video games and for lighting code as well, for graphics. And this example will show it. Let me copy that. We'll paste this in. And let's walk through the code before we start here. So we're just setting up a window, frame buffer, world, camera. Okay, we're going to load this ship 3D model from our documentation. And we're going to create a mesh cone called view cone. We're going to rotate this 90 degrees and move it forward. So we're mounting it on the front of the spaceship. And we'll create this enemy box. And we're going to position it at position 0010. And then okay, here it is. So we're going to call transform normal 001 ship null to null. Okay, so what this is doing, we'll have a whole lesson about this, but this is getting the forward direction of the ship. It tells us what the vector is that points forward relative to the ship. And then we're going to get the dot product between that direction and the delta position, which here we are defining that as, let's see, delta position equals the enemy position minus the ship position. So this is vector subtraction. This is an example of vector subtraction. That gives us delta position. We normalize that. And then we're getting the dot product between the ship's view direction and the vector between the ship and the enemy. So if that was confusing, that's okay. Yeah, I think it's easier for me to just show you. Okay, there's our ship. Here's the cone that we set up, our view cone. And this yellow line here, this shows the vector between the enemy position and the ship position. So this vector is delta position. Okay, now you can see I've got another vector here. This is the direction vector that indicates which direction is forward for the ship, right? These are two vectors, this right here and this. And I'm using the dot product to see how similar they are. Now, I can actually convert the dot product into an angle with the arc cosine function. This is a trigonometry function. If you've taken trigonometry, then you'll learn about this. If not, just know that a cosine will convert a dot product into an angle. And I'm saying if the angle is less than 45, then I'm going to set the enemy's color to green, which is 010, because that's RGB. If the angle is greater than 45, then I'm going to set the enemy's color to red, because that's red, green, blue. So red is fully lit. So right now that angle is greater than 45, and so the enemy is colored red. So this is basically outside of my view area. And see that? As soon as it goes inside, as soon as the center of that object goes within that 45 degree range, then it changes green, and I can use that to tell whether the ship can see this object. You can adjust this view cone to be whatever value you want. But this is a very common technique to tell if one object can see another. So you can use this to program enemies. This will allow you to sneak up behind them if you stay out of their view area. And then if they turn their head towards you, then they become aware of your presence. So the dot product is extremely useful, and it's all just vector math. We have another function that you might find useful, and that's the reflect function. And I have an example that uses that. Paste this in. And what I'm going to do here is I'm going to set up a laser beam that's going to shoot at the ground, and then it's going to bounce off the ground. So the first beam is going to be colored red, and the second beam will be colored green. So the second beam will be oriented based on the reflection vector. So, and that's right here. That's being called right here. So the direction vector is vec3, 0. So that's the origin, minus the laser position. I'm setting the laser position up here to be 330, and I'm going to be able to move it around with the keys, with the arrow keys. But you have that direction vector, and then we're going to call reflect. And reflect will accept one argument. It's another vector, and that the other vector is the normal of the ground that we're bouncing off. And since we're bouncing off the ground, it's going to be pointing up. So the normal is 0, 1, 0. And that will give us our reflection. And that tells us how to orient the bounced laser beam. And there it is. Now I can move the laser position, that's this value right here. I can move that around and adjust it, and the reflection will adjust. So I'm kind of rotating it around right now. So that's a simple example of the reflection method, and you can use this for laser beams or many other things. So that's all I have to say about 3D vectors for now. If you've taken geometry in school, then that will certainly help. And I think it might help to be able to see some of the ways that these things can actually be used. But this is fairly advanced material. So if you need to go through it a few times, that's okay. If you have any questions, we'll be available on the forum and on Discord. And I'll see you in the next lesson.